So welcome again. Let's just proceed with our next larger topic inside exercise sheet 10.1. Everything here is about path integrals. So path integrals are still another special kind of integrals of you could say of a multi-dimensional sort. In a sense that a so-called path may be, in the most interesting case, maybe a three-dimensional curve, even a closed curve, or a curve which turns around itself, like a spiral. You remember, we have been concerned with such kinds of curves already, and have called the way of describing them a radius vector function. Also here, this is the case. As you can see, the first exercise is a little more extended. It puts in quite a lot of different functions. Here you see it's a 2D case, so not only is the curve we are concerned with here a planar curve, but also the same holds for a certain vector field, as you can see here, and yes, you could say a corresponding potential function, a scalar function. All these functions are defined in a two-dimensional vector space, as we've seen before. But on the other hand, although this is the most extended exercise, it's also the only one in 2 dimensions. Everything else will be 3-dimensional. So we'll see. What is it about? First of all, I must tell you, I wish to tell you that we discriminate two quite different kinds of path integrals. Before I explain what a path integral is, which you should know, of course, but I will repeat. More precisely speaking, it is possible to integrate certain scalar properties along such a path, such a curve. It doesn't make so much difference talking about curves or paths, but this coining has been most commonly used. So there may be certain undirected properties to be summed up continuously along the path. Then we are talking of a scalar path integral, which means, more in detail, well, integrating a scalar function along a path. And well, this is one possibility. The other possibility is to take a vector function like this one and find out by calculation which is you could say which is the contribution this vector field brings about along this curve. And now in this case, it's very important to understand that only the component of the vector of the field vector in tangential direction along the curve counts. And this is what we've been familiar with already, taking the scalar product of a vector with another vector. So we would take this field vector and then construct the scalar product with the tangent vector of this given radius vector function. Everything sounds complicated, but it's just that's the way it is. So please don't be confused about the fact that in both cases we get a scalar result. We never get a vector as a result, because in the case of a scalar function, it will be, well, just the total contribution of this scalar along the path. And in the case of a vector path integral, it will be the same, namely the contribution of this vector field along the path, in the sense of the component of this vector along the path. It's also possible, theoretically, to do different things, but this is all we are concerned about. Now, let's just dive into this setting here. First of all, you see there has been a typo here with a factor of 3. Instead, it should be a factor of 4. This has been corrected in the meantime, so don't care. The typo has been removed in the currently uploaded version, PDF version of this sheet. So what do we see? We see that path P is defined as follows. The radius vector equals 4 times, so this is just a scaling factor, this interesting 2D vector here, which consists of cubed versions of cosine and sine for the first and second component. And when this was examined for the first time, it was just sort of a variation of the well-known unit circle, as you know, cosine t, sine of t. Then people were considering different exponents instead, like squared versions, cubed versions, and so on of cosine and sine. And in this case, quite an interesting curve resulted, which is now called an asteroid. This is what I gave you here, and I hope you found the time to to have a little look inside Wikipedia, where this is described very much in detail. This is not the topic we are concerned with. This is just a side note, so don't worry. You don't need to be an expert on asteroids. I find it interesting alone looking at this phrase, because it sounds like asteroid. Please don't mix it up. Asteroids, as we all know, are certain kinds of dwarf planets in the solar system. This one has a very similar name for a simple reason. In both cases, it goes back to the Latin word for star, which is astrum. You may have heard the saying per aspera ad astra, per asperum ad astra, I think, or how is it called? Per aspera ad astra, yeah, something like this. Ad Astra has also been a current cinema movie with Brad Pitt starring, quite an epic film about a space journey. Even quite a good film, I would say. So, why is it about stars? That's the question. And well, we'll see soon, because the first task will be to draw a little sketch of this curve. Also, I must inform you that path P is well, actually, we look at 2 different subpaths, you could say, along this curve, where the first one goes around once, around this closed curve. The other one goes the other direction, and it only covers part of this curve, and that's for a special reason. So this is everything I'm telling you now is just a preparation. Well, now you may wonder why this seems to be the same as this one. There are different approaches to understand this. One of them is, if you remember your learnings about complex numbers from the first semester. And then there is the famous Moivre's theorem. You might remember. It's like this, Moivre's theorem of complex numbers. And this is a certain way of describing either the polar form or the exponential form. And there we found out that multiplying complex numbers means adding their arguments. So, and that's why using Moivre's theorem, it's possible to easily reproduce all, and this is quite a lot of such identities, all sorts of sum to power or power to sum identities for cosine and sine. And also, if you look here, so-called power to sum identities. This is one of them. And the next line, it's another one. And all these come about by using Moivre's theorem. This is one way of understanding it. The other way is recognizing a close correlation, or a close, yes, you could say close connection between this transformation and the so-called Chebyshev polynomials. Also, this is just for your interest. So if you ever heard of these famous special polynomials called Chebyshev polynomials, this refers to the third first-order Chebyshev polynomial. You may also look it up on Wikipedia if you just want to widen your mathematical horizon, but it's not necessary, okay? So that's the reason why it's possible to make this transformation. It turns out that inside our exercise, sometimes this is advantages to use, and sometimes this one. Okay, we'll just find out. So now let's just go into the first one. And as I told you, this asteroid curve Did I? I think I called it before starting. I told it before starting the recording. This is also a special kind of a so-called cycloid curve. And if you look here, you can understand why. You should remember that we were looking at the standard cycloid curve not long ago, where we had a horizontal line, roughly like this, and then a little circle rolling along this line, rolling along by turning around itself. And then there was a certain mark on this rolling circle, and this way the so-called cycloid trace originated. This is a very, very bad picture now. It's just for your for your remembrance. Okay. So, and looking here, we see that this can be varied in a huge kind of different ways. What I want to say is, why not take a small circle and have it roll around another circle? In this case, on the inside, you can imagine, right? Starting here, and then just, so this, by the way, it's a unit circle. This will turn around itself clockwise, but at the same time, it will roll along the blue circle counterclockwise. If you construct it this way, and again, we have a highlighted point on the circumference of the smaller circle. And also it's important that the ratio of both radii is 1 to 4, right? So if this is a unit circle, the other one is a circle of radius 4, it will turn out that this highlighted point leaves a trace corresponding to this red curve, which has obviously 4 nodes. Here, these are special kinds of singularities, always called cusps. You may remember I had given you this phrase a while ago. They are called cusps, and it's important to know that only if your highlighted point here sits on the circumference, you will produce such cusps. It would also be possible to take another mark inside this rolling circle, and then you will have the effect of rounding. So it means that these cusps won't appear anymore. It will, the curve will look smoother in comparison. But now about the coining asteroid, it's very simple. For some people think that this kind of curve looks a little bit like a lighting star, with, of course, a very naive kind of drawing. Yeah, I'm talking of stars as celestial objects. Some also call it carreau. That's the French word, and also in playing cards, this is used as a symbol, as you may all know. So constructing it and then just mathematically examining its features, we find out, look at the black curve here, starting in point A, there will be, well, a walkthrough this way, counterclockwise, from A over B, C, D, and then back to A. All these special points, these cusp positions, are intersection points to the axes, coordinates 4 or -4 respectively. So this is quite obvious, okay? So the black curve will be once around. The reason is, look here, that T is increased starting from 0, ending at 2 pi, while for P2, we have T decrease starting from pi half and ending at 0. And so that's why the blue curve, this is P2, path P2, subpath if you want, starting in point B and ending in point A. So this is an open curve, the blue one, while the black one is closed. Now, the second. Well, we should verify that P1 is a closed curve. That's relatively easy. It's not as easy to verify that it is a simply closed curve, not intersecting itself anywhere. We might do this, but it takes too much time, so we leave it away. And then we are asked to calculate 2 features of this closed curve. 2 interesting features, of course. Firstly, its circumference. Oh no, it starts with A. Okay, firstly, where is it? Okay, I see. Look here. This is about the area that is enclosed by this curve. And we are asked to calculate the value of this area, which is called A here, and also its circumference. So now these are two quite different questions. And I'm not sure, but I suppose you did not learn how to calculate the area inside a closed curve if this curve is described as a radius vector function. And since I thought it's interesting anyway also to exercise the techniques of path integrating, I present you the famous Leibniz sector equation. So this would be an allowed tool for you in this case, just to use this scheme. It has been proven, of course, by Leibniz. It's quite interesting to use this symmetric form. Theoretically, it would be possible to use only this x, y dot term, and either only this one or only that one, x dot y. But it turns out that it's, in most cases, it's better to use this combined expression because the integrand will simplify. Well, this is the case here, and often, generally speaking, very often, but you might also use other forms. So this just tells us that the enclosed area will be 1/2 integral from T1 to T2. This is nothing surprising, just the starting and ending value of the parameter T, sorry. And then integrating this term along this range of our independent variable T. So the term is x y dot minus x dot y. And this, of course, refers to the two different components of the radius vector in the radius vector function, using this or using this, as you like. So dot always means taking the derivative referring to t, and the rest is just doing some algebra. Also, we have another hint here, which is a certain of the before mentioned product to sum identities for cosine and sine. You should know these two. They are probably the most famous ones for replacing a certain product of cosine or sine by sums or differences of special cosine terms. There are two more variants of this, but we only need these two. So that's our topic now. And look, why is P1 a closed curve? Well, that's rather simple. We just take our starting value for t and the end value, which are 0 and 2 pi, and then just insert. And you see that the cubed cosine of 0 is 1, of course, because cosine of 0 is 1, and 1 cubed is still 1, while the sine of 0 equals 0. So we get 0 in the second component, but then everything scaled up with a factor of 4. So we end up in 0.40. This is our point A here, and the same again, inserting 2 pi for t. That's easy because we all know that cosine and sine have a periodicity of 2 pi. So it's very clear that the endpoint of the curve will be identical to the starting point. So that's why the curve is closed. As I said, it's not so easy to show that it's just simply closed and does not intersect itself anywhere else. But it's true. we don't take the time and effort to prove this. So let's look at the enclosed area, which is then, due to Leibniz sector equation, the following. Now you can see that I obviously switched to the second representation for certain reasons. You might try both ways, but it turns out that using this, it's a little bit easier. So what do we see? It's just a fact that cubed cosine of t is the same as 3 times cosine of t plus cosine of 3t. Now just taking the derivative, is it? Let me think. Oh no, I think the first term is x times y dot. So we just take this over, and then we take the derivative of the second component. Just try and keep it in mind. 3 sine of t minus sine of 3t. Okay, let's just take the derivative right now. So here it's easy. Derivative of sine equals cosine. So we have 3 times cosine of t. And then minus 3 times the cosine of 3t. Why did I say 3 times? Because in this case here, we have to use the chain rule of differential calculus, because the inner argument is 3t, and so the inner derivative will be a factor of 3. And now look here, this is why I wrote, oh, did I? Yeah, here it is, this factor of 3. So once again, this is just the x component of the radius vector of our curve description as it is, and then multiplied with y dot. And y dot, as I just told you, is equals 3 times cosine of t minus 3 times cosine of 3t due to the chain rule. So that's the first part. Then minus, and this time the first component must be differentiated for t. So now look here, this is still the original x, and we want to construct the x dot from here to here. So the derivative of cosine of t, as you all know, equals negative sine of t. That's why I get negative 3 times sine of t. Please note that this factor of 3 was there from the beginning, also here, while the other one just appeared due to differentiating. Okay, don't mix it up. So from here to here, constructing x dot out of x, the same holds here. Cosine, derivative of cosine equals negative sine of 3t in this case, but then again, factor of 3 for taking into account the inner derivative. So the derivative of the inner function, 3t, which is factor of 3. So that's the x dot, and then times y as it is, 3 times sine of t minus sine of 3t, that's all. And now, of course, it's just a little time-consuming to remove the parentheses here, which I'm doing right now. And you please do me the favor and follow me in detail. So we have a prefactor of 1/2. I just leave it alone. Then we have an integral, of course, from 0 to 2 pi to be evaluated in the end, and then building all the products. Now, 3 times cosine of t times 3 times cosine of t. So this is the square expression, the square of 3 times cosine of t. Well, easy. 3 squared equals 9, cosine squared of t, and that's it. So this was the first times the first. Now I take you might use your scheme. This time I use the following scheme. I move on to the second contribution here, but stay with the first here. So now I multiply this one with this one and get, always pulling constant factors to the left. Okay, so I get 3 times cosine of 3t times cosine of t. That's this one. So now, well, this was first times first, then second times first. Now I take first times second, so I'm here, 3 times cosine of t times negative 3 times cosine of 3t. That results to negative 9 as a factor, and then cosine of t times cosine of 3t, this term. Then second times second, cosine of 3t times negative 3 times cosine of 3t. This time I have cosine of 3t here and here again, so this one squared is what I get, and a factor of negative 3 only. The same procedure here. Look at it's almost the same if you look, every cosine is replaced by a corresponding sine, but sometimes there's a minus here, and here it's not. For example, this plus is replaced by a minus, so we should really be careful in the end. And also, please don't overlook this one. This is due to the scheme, the negative sign here. So take care. We get minus, plus as factors. So minus 3 times sine of t times 3 times sine of t, which means in the end, it's a positive contribution. We get plus 9 times sine squared of t, definitely. Okay, but then, okay, always keep this in mind. First times, no, let's say second times first would be negative 3 times sine of 3t times sine of t. So negative 9 times sine of t times sine of 3t, or the other way around, this one. But the negative sign gets, I always, okay, you know, sine as a function, and sine as a sine. It's the same words of written differently, but pronounced the same. Sine and sine. You know what I mean? This is the function. This is something different. This is plus or minus. Okay, you know what I mean. Anyway, we get, where was I? Here. Well, let's do it all over. Negative, negative gets positive. Okay? Minus, minus gets plus. 3 times 3 is 9, and sine of 3t times sine of t. So I'm here. This was reproduced right now. And then we go back to, do we? Yes. Back to the first here, and now times the second. And this time I get minus, 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 so the minus stays alive. And I have negative 3 times sine of t times sine of 3t. So, and there I exchange the factors. This might be a little bit confusing, but this is what I took right now. And finally, I get minus, 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 so it's minus again, staying alive. And then 3 times sine of 3t times sine of 3t. So this time again, we have a squared sine of 3t. Cool. So, but that's all we have. And now you see, I underlined these squared versions of cosine and sine of t in blue color, and these squared versions of cosine and sine of 3t in violet color. Why? Well, simply in order to simplify this expression as much as possible. And we all remember almost every time if we get squared sums of cosine and sine of the same argument, this is always equal to 1. So we have to, first of all, of course, we have to put it in parentheses. We can easily do because the factor of 9 here and here is the same. So this is actually 9 times the squared sum of sine and cosine of t, and inside the parentheses we get a factor of 1. So 9 is all we get. Okay. These mixed terms are similar pairwise. Look, this one and this one. So it's the same factors here and here, but also 3 times the whole expression minus 9 times the same expression. So altogether it's minus 6 times this expression. And then I sorted it, okay, like cosine of t times cosine of 3t. Also, then the same here, 9 times this expression minus 3 times the same expression. So altogether plus 6 times this expression, which is sine of t times sine of 3t. Also here, I exchanged the factors for reasons of systematics, okay? Finally, here and here, we can put this into parentheses, the squared sum of cosine of 3t and sine of 3t, which is also equal to 1. So the factor of negative 3 remains. That's all we have to integrate over t. And that's what I do. Let me see. Yeah, also, of course, taking together this constant with this pure constant. 9 minus 3 equals positive 6. And then splitting up the integral, which we are allowed to do, of course. So we get 1/2 as a global prefactor times integral from 0 to 2 pi, and then just a constant 6 over dt. That's simple. Minus now all the rest, which is again 1/2. This factor holds or is valid for all this for all these terms. So it remains. And here I pull this outside and also the factor of 6 since it's constant. From here and also later from here. So I have 1/2 times negative 6, which is negative 1/2 times 6, or shortened negative 3 in the end. Then times integral from 0 to 2 pi cosine of t times cosine of 3t dt. This is from here. And then even more, well, splitting up here and again here. The rest of it is 1/2 times, look here, 6 times integral sine of t times sine of 3t. And that has been put together with the 9 minus 3. So that's all. But now we must ask the question, what remains of these? Or in other words, is it possible, is it easily possible to perform these two integrals? Well, actually, this is why the hint was given to use these product to sum identities, which we may do. But honestly speaking, with a little thinking, you might argue that it is quite clear beforehand that both these integrals will be zero in the end. Well, but this is a little tricky. You would have to argue that the product of by the way, first of all, from 0 to 2 pi means we have a whole period of this cosine. And we all know that the cosine and also the sine of t are so-called purely alternating signals. What I mean is, speaking a little bit electrotechnically, they have no bias. They are unbiased. You know, the DC component is zero. You know what I mean, I hope, from electrical engineering. So that's why the area, just ignoring this factor for a second, okay? The area of this function graphically between 0 and 2 pi, the area between this, the graph of this function and the t-axis, the time axis, let's say, will be 0 because half of it is above axis and half of it is below. So I'm talking about the positive and negative semi-waves of cosine and sine. But now the same argument holds for cosine of 3t. As you know, this is scaled down by a factor of 3 horizontally, if compared with this one. But it means that it still has at least a periodicity of 0 to 2 pi, of 2 pi, sorry. Actually, its main period will be 2 pi over 3 only, because it's squashed, you know, by a factor of 3, horizontally squashed. But this doesn't change the fact that also this term has a perfect, alternating characteristic, which means it's also unbiased. Also, its area between its graph and the t-axis will be 0. And then multiplying these two will also give you a totally unbiased signal, which must mathematically have an area of 0 over a whole period of from 0 to 2 pi. So that's the more, you know, the how should I say, the graphical argument. It holds for this one, also holds for this one. Same thing for sine of t. So you could say it's not even worth the effort to solve these integrals. But let's, for security or for safety, let's just do. So it's not really hard. Look here, taking these hints, then dividing both equations by 2, as you see here. So this factor of 2 disappears on the left side. Then just identifying alpha and beta, or alpha and beta, with t or 3t respectively. My choice would be alpha equals 3t, while beta equals t. If you then look here, in this case, alpha minus beta will be 3t minus t, which is 2t, and the sum of alpha plus beta will be 4t. And that's what I did. Look here, 2t, 4t. I mean, 2 times t, 4 times t, okay? And then, but also this factor of 2 gets moved to the other side as a division by 2. So it would get a prefactor of 1/2 here and 1/2 there. And then just try and solve it in your head. Since the argument is 2t here, solving the integral for this part, we would have to do the opposite of taking the inner derivative.
Professor?
Yes?
So instead of this, like for cos t, cos 3t plus sin t, sin 3t, you could directly use cos of a plus b formula.
This was a little fast speaking, so I didn't quite understand. Are you asking if you can take an abbreviation here?
Yeah, like
No.
instead of using these two separate formulas, we could just use cos of a plus b formula.
Okay, but in the end, I think it's the same thing as I'm doing. So I think you're on the right track. Okay?
Yeah.
Yeah, probably. I just want, and okay, let me just put this to an end. I just wanted to explain there would be sort of a factor of 1/2, first of all, would be here, but then taking the integral, because this would be replaced by 2t, I would have to divide by t, the whole thing, you know? like not taking the inner derivative, but the opposite. When integrating, I have to divide by this factor of 2. It's called a linear substitution. That's the official coining. But that's what I do. I divide by 2, so I get 1 over 2, and again 1 over 2, so I get 1 over 4. That's what I wanted to explain. While here, where this is replaced to be 40, I have to divide by 4. And since also here I have a prefactor of 2, taking this away, I get 1/2 divided by 4, which is 1 over 8. I hope this is the same as you've been saying. It's just a little more in detail, okay? So really, this is the primitive function of this one after using this transformation, and then evaluate it between 0 and 4 and 2 pi. And this is the latest moment where you recognize that, of course, also these modified sine functions have a periodicity of, well, a certain whole fraction of 2 pi. So in the end, they will be 0 everywhere. At 2p, not everywhere, but they will be 0 at 2 pi and also at 0. So everything's 0, and it's what you could say, had supposed before. So no matter how you do it, in the end you find out, well, let me wipe this away again. You find out the contribution is 0. I don't know who asked the question. Is that fine for you?
Yes, Professor. I just completely got your logic. I just thought the other formula would be like a bit faster. That's it.
You gave exactly the right remark. Thank you. And it's quite fun because all the complicated terms, well, just go away, and everything that remains is this, you could say, a trivial integral, which is just taking the constant 6 times the length of this interval, as you know. Okay, you could also say the primitive function equals 6 times t, and then you insert upper limit minus lower limit. In the end, it's 6 times 2 pi, which is 12 times pi, but then divided by 2. So 6 times pi, this is the result. That's the area enclosed by our asteroid curve.